is given by two speakers, Juan and Sokratis. Juan is a PhD student in the engineering fluids and thermal science group at Brown University. He obtained his bachelor degree in mechanical engineering from the University of the Fuerzas Armadas at ESPE in Ecuador. Juan began his research career as an undergrad by remotely collaborating with the university at the Buffalo on several projects related to machine learning modeling of the physics systems. Sokratis is a PhD student in the cardiovascular technology lab at EPFL. He is currently visiting the Crumbs group at Brown, and he studied mechanical engineering at the University of Bristol and computational science at the Imperial College. So you two may want to start a presentation. Could you try sharing the screen first?
Sure. Let's see if it works. Can you see our screen?
Yes.
Great. First of all, thank you so much for the invitation, and thank you so much for the nice introduction. Well, today Sokratis and I were going to present our recent work in this paper titled Residual-based attention and connection to information bottleneck theory in physics-informed neural networks. First of all, I'm going to give it like a brief introduction. We're going to talk about the motivation of the problem. What are the problems that we're trying to address. They're going to talk about the method, and we're going to introduce this residual-based adaptive method. Then Sokratis will give us will present some of our results, and we'll do this we'll explain this connection to the information bottleneck theory, and then we'll finally summarize our work. Okay, to start, for the motivation, why do we care about physics-informed neural networks? Well, in general, physics-informed neural networks offer an alternative to traditional numerical methods to solve partial differential equations. And how do they work? Well, the key idea, the key concept needed to understand is a neural network itself, it's a function, and it's a function that has an extraordinary capability to approximate to any function. So in this ping framework, we're going to have a neural network, and we're going to ask it to obtain the solution of our partial differential equation. And well, the idea is equation using automatic differentiation. And well, if this approximation is good, it's good enough, well, then we would be able to we would be able to satisfy the PD. And yeah, and well,
I'm sorry, is it me or the speaker's screen is?
Even I had the same question.
It's not you.
Oh. Oh, okay. Juan, are you there?
Can you hear us?
Yes, I think the internet was unstable.
Oh, that's weird. I think I'm connected to the Brown. Yeah, I'm the Brown one. Oh, I'm so sorry.
Sorry. You can try it.
Okay. Yeah.
Start after the first slide, probably.
Yeah, we have some internet issue.
The first one, let me try to say, cancel. What I'm doing. Sorry. Let me go again here. Okay, so can you hear me now? Please let me know if at some point
yeah.
Can you not turn off your camera? That way I can see you that you're there, and then I know that I'm still presenting. Yeah, or maybe because if you
I open my camera. Yeah.
Okay, thank you so much. Yeah, I'm sorry everyone for that. Okay, once did you were in the introduction? But I'm gonna start again. So and first we're going to start with a brief introduction. We're going to motivate this study through the PINGS framework. We're going to talk about the problems with PINGS, and then in the second part we're going to talk about the methods, and we're going to introduce this residual-based attention method. And then third part, Sokratis will present some of our benchmarks, and then he will try to make some connections with the information bottleneck theory that gives us some insights about how these things work. And then finally, we're going to summarize the work. once again, to go really fast through this part, is like, why do we care about physics-informed neural networks? Well, we care about them because they offer an alternative of traditional numerical methods to solve partial differential equations. How do we do that? How do we do that? Well, the key idea to understand pings is like a neural network itself is a function, and it's a function that has an extraordinary capability to approximate to any function, almost any function. And so if that's the case, we're going to have a neural network, and we're going to ask it to approximate the solution of our partial differential equation. Then from this approximation, we're going to reconstruct our PDE using automatic differentiation. And well, if this approximation is good enough, well, then the partial differential equation would be satisfied. We constrain this problem using some data that can come from some observations, from some boundary conditions, some initial conditions. And well, this model, this expression is quite flexible. So including like data from observations is quite easy. So solving inverse problems with pings is one of their main strengths. The idea is like physics for neural networks can integrate physical models in data. You have some examples when we solve the Navier-Stokes with using data. However, since we have like here, like in this case, 4 loss terms, it raises an issue. The issue is that we want to minimize them, but we need to know what is the right balance. Do we want to balance them? We want to minimize all of them at the same time. What do we want? But we know to need some kind of balance. We need some kind of order to avoid convergence or accuracy issues. To give you a bit, to go a bit more with that part, like let's assume here we have some flow in this channel. The flow will go from left to right following this green arrow. So here, for to solve it using a ping, we'll have 3 data sets. We'll have these red points that will be our boundary conditions, these yellow points that will be our data, and these black points that will be our residuals. These red points and the yellow dots will be labeled data, so we will actually know the ground truth, and these black points will just be points inside the domain. But we know that if they're inside the domain and they're in this fluid, they should follow in this case, the Navier-Stokes equations that are ruling this case, but it can be, depending on the problem, would be like the PD that you're trying to solve. So here, for example, here we have 3 loss functions, but they can be in different scales. So which one, how do you do it? And then that's one of the problems. So we want to do it right. And also another issue that we can have here, like for example, we have many points. Maybe we can have some regions that have some high error points. But since we're computing here, you can see that we're computing the mean. The idea is like, since we're computing the mean, the optimizer will care only about the mean. So if you have some high error point, let's say here's the high error points, but all the other points are low, well, the optimizer will learn to ignore that high error point because it only cares about minimizing the mean. So we need to pay attention to that, and how we address that problem. Sorry for that. How we address that problem is like doing 3 kind of things in general. Researchers have come up with many methodologies that can be roughly classified into these three categories. That it will be neural network modifications, some equation transformations, and some adaptive weighting strategies. And I'm going to explain a bit more about what each one of those mean in the next slides. But it's important to mention that to achieve a really good performance, usually we need a combination of the 3. It's not like you would pick one and everything is going to work perfect. Most likely it will not be the case. So let's go back to the methods. The methods, we'll start with these ping enhancements, which we're going to address the other 2 points, which would be the neural network modifications. The idea of the neural network modifications that we're going to try to address the multi-layer perceptron optimization capabilities. For this study, we used this technique called the modified MLP. And the idea of the modified MLP is that we're going to encode our inputs and we're going to feed them into our hidden layers. It's like doing some kind of residual connections into the hidden layers. For the equation modification, the idea of the equation modification is like we solve the problem by we simplify the problem by solving it on its homologous forms. For this case, we're going to use exact boundary imposition. How this works is, well, the idea is like if our boundaries are satisfied by definition, well, then we don't have a loss term related to the boundaries. So then our optimizer can focus on a single loss term. For example, here's how we can do it. For example, if we want to impose like periodic boundary conditions. So for example, we can embed our input into this feature embedding. And you can see, for example, here that this will be periodic between 0 and 1. If you fit 0 or you fit 1, you will have exactly the same input. And if you have the same input, well, you have the same output, and you're imposing periodicity by default. And you can also do it for the declared boundary conditions. You can do this. You can do it by using many ways, but for this case, we use this approximate distance functions by Suku, who was visiting around the current group in the last months. Well, the general idea, like in the normal ping, let's say that this U is the solution of the PDE, and we approximate it using the neural network. And well, what we do here is like now the actual solution in the ADF scheme framework will be like the solution of the PDE will be the we compose of two terms. First will be a function that satisfies the boundary conditions in the boundaries. So when you evaluate in the boundaries, you have the exact solution in the boundaries plus this distance function multiplied by the neural network. And this distance function has the property that when you evaluate it in the boundary conditions, this is equal to 0. So you can see that when you're in the boundary conditions, you're satisfying the boundary conditions by definition. So you get rid of a loss term. The last thing we can do here, and this is actually the main focus of this study, is like these weighting strategies. And the idea of the weighting strategies is modifying the loss terms contribution, or maybe like the loss sub-region contribution for the point I explained before during training. We can have some fixed, for this case, we have some fixed global multipliers. So we're going to add some these lambdas D, lambda B, lambda PD in front of the whole loss term. And well, why do we want to do that? We can do it for two reasons. Maybe we want to balance the loss terms. We want all of them to be minimized at the same time. Or maybe we want to prioritize some kind of sub-regions. For example, maybe we want to learn the boundaries or the initial conditions first. Well, in this study, as mentioned, we're going to focus on these adaptive local multipliers. And once again, the idea of the adaptive local multipliers, so like you're going to tell your model, well, it should focus. And here, let's go to our previous example. Let's say assume we have, once again, red points, boundary conditions, black points, residuals, yellow points, data. Well, we create some kind of attention mask. This is inspired by previous studies. For example, we have the self-adaptive ways, DASA pings. This has been done before. So the idea of using this attention mask. But the idea is like what I said before. We may have some point in which the error is high, but all the other errors will be low. So the optimizer will learn to ignore that point. So the idea of the attention mask is to explode the error in that region, so the optimizer can no longer ignore those high error points. So to do that, we create this attention mask, and then we do this element-wise multiplications, and we get weighted points. So we get the weights will be now inside of the actual expression. We can do it for all the boundaries. For all the data we have, boundary conditions or residuals, but for this particular study, we're going to focus only on the residuals. And we will have some requirements for this lambda I in the iteration K. First of all, the first requirement is that they should help us identify the high error regions. So to do that, we know that it should be a function of the error or the residual itself. They should be efficient, and easy to compute. And well, what is easy to compute? That the residuals themselves, we just put them inside the absolute value. But they should be stable. And for stability, we can do it like things like, what do we do? Like we normalize them. We normalize them per iteration. What we want is like the contribution of each iteration should be the same. And we multiply it by a learning rate. So we make sure that they do not explode in one direction or the other. They should be able to remember the previous iteration. So they should be a function of the lambda of the previous iteration. And they should relate to the current training state. So we'll multiply it by this gamma. The idea is actually, this is the important part here, is like, once we learn a point, we don't need to keep remembering. We do not need to keep giving it attention. So if we already optimize a point, and then we'd reduce the attention. And that's the idea of this gamma. This gamma will be a number less than 1, that as you go forward, if you already optimize the point, you will forget it eventually. Using all these concepts, that's how we formulate our scheme. This is like the general expression, combine all the things I said before. So the multiplier for a point I in the iteration k plus 1 will be the multiplier of the previous iteration, multiply it with this a memory term, plus some learning rate, plus the normalized, multiplied by the normalized residuals.
Can I ask you something? You say attention, and it makes everybody immediately think of attention and transformers.
Yeah.
Is there a connection? There will be one as you keep on discussing?
Yeah, actually, as I said before, for this work is, for example, inspiring the self-adaptive weights. The only difference that for this case, this attention mask is trainable. These obtain these lambdas, they do it by training, but they inspire their work. Their work is inspired by the transformers. So yeah, you're right. So you got it.
So you will discuss in which way it is inspired by the transformers, or you just call this also attention? It is colloquially it is attention, but will you discuss how it pertains to attention as in transformers?
No. I will not discuss how it pertains to attention in relation to the transformers. We're just saying that we focus on that.
Okay, one more quick question. Will you discuss the relation with the adaptive pins from Ulises Braga Neto? There was another paper and talk some time ago. Does this fall somewhere? Will it appear somewhere, the adaptive, self-adaptive pins, as they're called?
Those are the self-adaptive weights, the ones I just mentioned. The relationship is like here, when your attention mask, these multipliers are trainable. And
there is a relation between this and the paper by Braga Neto and students?
It should be, of course. Okay, it should be. Yeah, it should be. You see, for example, here they have the maximization of the residuals that they do. If you wanna go in that part, the only difference that you could find, for example, here is like this memory term, that they do not have it.
Okay.
The residuals, they do not do it with the residuals, they do it for the gradient of the loss. So yeah, okay. But it's related, and actually in the if you go through the manuscript, we cite them and give them the proper gradient.
Okay, thank you.
Okay, thank you too. Okay, so once we have the overall expression fulfilling all the previous conditions that we explained, this is how we train the model. And for example, now we have the expression. We initialize their weights, the network parameters, and we initialize our lambdas with 0. This is another maybe difference with self-adaptive weights. In the self-adaptive weights, you initialize them with random numbers, and the idea of the initializing with random numbers is, and if you play with it a little bit more, is like they can become a bit unstable depending on the initialization of your weights. In this case, they are purely deterministic. So you are 0, you started with 0, and you just keep adding where you should add. Then we have for every batch, you compute the residuals, you compute the error, you update your lambdas, you compute the loss of the residual, and then you compute the total loss. Once you compute the total loss, you update your gradients using the traditional gradient descent. Another thing that I was going to mention here, like by this expression, we can see that our lambdas are going to be constrained. Between 0 and our learning rate over 1 minus gamma. That's the biggest they can go. So another difference with self-adaptive weights, for example, that these weights are bounded, and they have the ability to decrease once you optimize the point. The advantages, they're deterministic schemes. They are bounded. We don't have exploding multipliers. We can maintain the relative scale between the residuals and the boundary constraints if you have more constraints. There are no training or gradients involved, so the computational cost is none, almost none. And since we focus on the residuals, well, then you guarantee attention on the fronts where you want to, where you guarantee that you're paying attention to the part that need to be paid attention through the residuals. Now Sokratis will continue this presentation, but thank you so much for your time.
Hi everybody. So Juan, how do you move this like this again?
Make this again. Myself, maybe you want.
No, it's good, but it's
like that better?
Yeah, sure.
Okay.
So
sorry. Yeah, go ahead.
Okay. So as Juan discussed, once we decide how we want to deal with the initial condition and boundary condition constraints, either through some static or dynamic global weights, or some exact boundary position methods, we can then focus on the interesting part of the domain, which is the internal points we want to solve the PDE for. And for these points, many people have tried to use these local multipliers, local weights for each collocation point I. And why do we need these local residual weights? Why are they important? So we can think of three ways. The first one is for convergence stability. So especially in stiff problems, we will notice this behavior that you will see in this video. This is for the 1D Alenkhan case. It's a benchmark we will discuss a bit later. And for example, here's the residual history as we move on in training. You can see it's quite unstable. So this could be especially difficult for an optimizer to follow. So we need to have some kind of stabilization multiplier for this type of noisy residuals development. Then they can also help us focus on the challenging regions of the domain, which consistently score a high residual value compared to other regions that are not so challenging of the same domain. And finally, it's important for propagation of information in order to satisfy the causality imposed by the initial or boundary conditions. The information flow from the boundaries and initial conditions inside the domain is very important and it needs to be propagated in an efficient manner. So with that, I will step right into some of the benchmarks. The first one is a very common benchmark that I'm sure many of you will be familiar with. It's the 1D Alenkhan equation. It's considered as a stiff problem, especially for the vanilla pin formulation, as it is characterized by these very abrupt transitions, and it can be regarded as an inverse diffusion in some ways. So here we have these boundary initial conditions. For the boundary conditions, we impose a periodicity. We exactly impose periodicity through the Fourier feature embeddings, as discussed previously by Juan. And in the objective function, we only have an additional term for the initial condition multiplied by this 100 to initiate the scale difference we want, which is consistent with the relevant literature. And in this way, we're able to directly compare with the best performing models of the literature, which use exactly the same formulation. And as we can see, the RBA weights, even though we don't train anything, they're pretty efficient at achieving a relative L2 error, which is very, very satisfactory, and compares with the best performing models of the literature. And I just have to mention here that the relative L2 error is basically a metric for the difference between the exact and the predicted solution, as you can see on the top right figure, which quantifies the relative error, basically. Now for this, so an important step for this work was for us to understand how different components that Juan discussed influence the final result and the convergence in general. So we can see here from top to bottom, as we keep adding more components, we increase the relative L2 accuracy. The y-axis is the relative L2 accuracy convergence as we move forward in iterations. And the RBA weights scheme can initiate an early convergence trajectory without any additional components. As you can see in this figure, when we add the modified MLP architecture with the feature embeddings, we can get an acceleration, especially for the first few 100,000 iterations, the first 100,000 iterations. But the important feature here is the formulation of the exact boundary conditions, which for us, it seems to be very important for these benchmarks that we will show. And in general, it's acknowledged as a very big improvement, significant improvement for the vanilla pin formulation. But we can see that the combination of all the three different components, both the residual weights, the modified MLP, and the Fourier feature embeddings for the periodicity, give us the best performing model, which is in the order of 10⁻⁵, as I showed you earlier.
Can I ask again something here? So you are changing all the time what your residuals are, and the L2 is reported on what you are working with, I assume, every time. Is there a corresponding plot, or would it look the same if you looked at the L2 distance from, let's say, a true solution or a very close solution to true on a regular grid? The reason that I'm asking is that you are indeed showing L2 changing, but what you are calculating the L2 of is changing, right? Because you're adapting the residuals at every step. So what I'm asking is there a way of looking at some sort of non-adaptive error? Am I clear in what I'm asking?
Of course, yeah, I understand. This is the relative L2, which is basically the prediction of the network as opposed to the exact solution. So there is no.
Okay, so this is the L2 of the error, not the L2 of your update or your. It's not your residuals going down. It's the distance from the truth going down.
Yeah.
Okay, thank you.
And it's the usual definition in the literature. The relative L2 usually means the relative L2 between the prediction and the exact solution.
Okay.
So Sokratis, this is Zuko here. One more short question. In the previous slide, how sensitive are the results to the 100, the choice of 100? And how did you choose 100? Why not 10, 1,000 or something else?
This is an empirical coefficient, which is very often seen in these type of problems. And even in the self-adaptive weights, indirectly, you can see this multiplier for different problems as you need to initialize your weights. For example, the weights for the residuals are initialized from 0 to 1, and the weights for the boundaries or the initial condition can be initialized from 0 to 100 or 0 to 1,000. So this is indirectly a global multiplier, an empirical multiplier, which is case specific, right? And we've seen ourselves that this kind of multiplier, if you choose to have this term here and you don't incorporate it in the PDE through some exact imposition, if you choose to have this additional term, you need to have some kind of scale, relative scale when you start your training. And this is important.
Because I was wondering, because for different problems, you might need a different starting point or different number, or you can always use 100, or that's what
it's totally case specific. And for this case, we copied basically through this term, we're able to directly compare with the top performing models, which both use this multiplier.
Oh, okay, thanks.
One more quick question, sorry.
Sure.
What are the nonlinearities in your neurons?
It's tan H, hyperbolic tangent.
Okay, so one of the parameters is where the inflection point of the tanks are. And so as you change, as you optimize, and especially as you change the weights, in some sense, the location of your basis functions is moving around. Am I right?
I suppose so.
Okay. Do you have a sense of, or have you considered which way the locations, I'm going to say supports is not necessarily a good word, but where does the support of your basis functions go compared to, let's say, the stiffness, the sharp gradients, and so on and so forth? Do you see what I'm asking?
I think so, yeah. We didn't really play with activation functions, and there's many things that one can do, like
No, not the nature of the activation functions, but where they are, where their inflection points are. Do you find more basis functions locally close to the sharp fronts, for example, as you keep changing this?
That's a good question, and it could be an interesting idea for a parametric study on these multipliers.
Okay, thanks.
For now, we're just using a constant global fixed multiplier, which initiates the appropriate scales, the initial scales between the initial condition and the PD loss.
Have a question here. You mentioned this is like a random problem dependent number, but it's been shown that essentially it correlates strongly with the gradients, right? Because what we want to achieve is we want all loss terms to be trained equally well. And when you do the gradient comparison, you're going to see that, for example, PDA loss, as was shown by Sifan's paper, has the highest gradient, and so therefore that drives the learning at the constant. So two questions. I'm not sure if it's quite random. And then the main question, have you tried initializing from the gradient perspective? Yeah, you forget about that gradient weighting strategy. You're using something else, but initialize the weights based on the gradient scales.
That's a very good question, actually. And it falls back to the answer I gave with the self-adaptive weights. So in the self-adaptive weights, you basically use the gradients, right, to balance these different scales between your loss term constraints. But you need to initialize them properly, because if you don't initialize them and you only rely on the gradients, you will not start the optimization process from a nice point. And what do I mean by nice point?
What do you mean initialize? Because, for example, with the gradient scaling, essentially you look at distribution of gradients and you rescale, you find weights that would result in a gradient distribution for all loss terms that are more or less similar. There is no initialization, no?
Not necessarily, because if you rely only on the gradients and you apply the self-adaptive weights without initializing in a different range rather than 0 to 1. So if you initialize all your lambdas from 0 to 1, in most cases, it will not work. You need to give the right kick, let's say, to your optimizer to start at the right point. And then you can work with the gradients. But from our experience and from the literature that we've seen so far, in many problems, especially stiff problems, where the initial conditions are very important, you need to initialize them with this empirical multiplier, or avoid including this term once and for all by imposing some exact boundary conditions. I don't know if that answers your question, but it's very reasonable to think that the gradients themselves can be enough to handle any relative scale differences. But
gradients are not necessarily from 0 to 1. If you check the gradients, they can be, for this problem, for example, they can kind of point exactly to this issue. That's what in Sifan's paper we find, right? So some of the weights from gradient scaling going to be 100 times or 1,000 times larger than, for example, the residual weight.
It's not 0 to 1. It's the value, the initial value of the multipliers. In self-adaptive weights, it's the initial value of the multipliers themselves, which are from 0 to 1. But if you don't initialize them appropriately, depending on if you're dealing with a boundary condition or residuals, the problem will not converge, even if you rely on the developing gradients, as you mentioned.
Okay, yeah, I will think about that. Thank you.
But it's still an active area of research, and we're working with that, and it's an interesting topic that interests us as well. So thanks for the question. So to continue with the second benchmark, I hope this is clear. The ablation study, which really shows how different components affect the convergence. Oh, here just one thing to mention. If you can see the two best performing combinations, which achieve the lowest L2, are associated with some kind of noise. And this is interesting to us because we see it often in good performing models. And we believe that this is due to the optimizer effectively skipping past local minima to find an even better solution. And this is important because otherwise you see that if your optimization process is very stable, you might get trapped somewhere that is not really low in terms of relative L2. But if you have a method or a combination of methods that is able to effectively navigate through the loss landscape, then you will eventually reach to a better solution. Just a small remark. And now for the Helmholtz equation, this is also a very, very common problem, not as stiff as the Allen-Kahn, but it's a common benchmark. And we decided to use this because it gave us a really nice representation of the bottleneck, as you will see in the later slides. But for this case, we used two different objective functions. So we have two different cases, basically. In the first case, to follow the literature of DASA pins and be able to compare directly with them, we use the same objective function where we deploy the periodic exact boundary position with the Fourier embeddings again, and the additional loss term of the boundary condition with the same multiplier 100 that we discussed. And because of the sinusoidal nature of the analytical solution, we decided to deploy the approximate distance functions here and reduce the loss terms to only the residual term. And for both these cases, we show the results here, which are in the order of 10 to the minus 5. And again, we can see that with a relatively simple residual-based method, we can achieve, and combine, of course, with the boundary impositions, we can achieve a pretty satisfactory comparison with the relative L2, the best performing relative L2 of the literature. And now I will, apart from all these benchmarks, what was interesting to us while running all these cases and the different combinations was that in every one of those cases, we noticed this abrupt change of the weights, the RBA weights, from a very ordered state to a very chaotic state. And this was interesting to us because sooner or later, in any combination we did, in any case we ran, we would see this behavior. So this kind of behavior reminded us the information bottleneck theory explanation for how deep learning algorithms work, and that they are dominated by two distinct phases, the fitting phase and the diffusion phase. So we try to make some correlation with that, which I will show you right now. So again, this is what we were seeing for the first phase, the fitting phase of training. So these are the RBA weights of the residuals, which obviously follow the information flow dictated by the initial condition, which is applied on the left boundary. However, at some point, the weights start behaving in a chaotic manner, focusing on very unregulated areas of the domain, while the relative L2 continues to decrease, which means that the weights are doing their work. It's just that the focus has changed, and probably the process of the network itself has switched in some sense. So just a brief introduction for the bottleneck theory.
Hold a moment. Can you explain what we are seeing in the two plots?
Sure. So in the left plot, we're seeing, in both plots, we're seeing the RBA weights. So it's the multipliers for the residuals.
Okay, so this is relative to the grid on which you calculate the solution. I'm a little...
Yeah, so you can imagine this as being very, very small points, but many of them, so we can create a contour of those points. So it's basically a scatter plot from which we've created a contour to show the dynamic behavior of those weights. But these weights are point-wise multipliers, which have point-wise coordinates in this domain.
But is it, I mean, I understand, thank you, but is it the weights that we should be paying attention to, or is it the parameters of the neurons that we should pay attention to?
Sure, and that's why, so it's basically the interplay between the weights and the residuals, first of all, and then second of all, it's also the network itself, and that's what we're trying to show here, that there is some connection to the gradients of the network with the visual aspects of the physics in neural networks, which is the solution and the collocation points and the residuals. But I will show it in the next few slides.
Okay, thanks.
Excuse me, I have a question. This is Panos Tinis from Pacific Northwest National Lab. So what is the horizontal axis here?
Yeah, actually, this is the domain of the solution. So The horizontal axis is
Is
basically
time? Is it time?
This is x. Time is so
The
x
hor-
is the time, and
Yes.
y is the x dimension.
And the two different figures that you show are at the beginning of the training and then further in the training, right?
Yes, exactly.
Okay.
We have
So
this later. So
okay. So so what you show here on the left is that at the beginning of the training, somehow the errors over all time, right, are somehow affected more by the initial condition.
yes, exactly. In a more ordered manner. And
which means what? That the residuals have not picked up yet to dominate the training, right? It's the initial condition that somehow dominates it.
yeah, you can look at it this way. Basically,
All I'm saying is that there is a bit of confusion, at least for me, because there are two times here. There is the time of the solution, which goes from left to right. And then there is the fictitious time of the training, right, which is the iterations. So if you want to talk about two distinct phases, fitting and diffusion, you're talking about the iterations of the algorithm as it trains, right?
exactly.
But there is an extra level of complexity here because you also have the temporal dimension of the solution.
Yeah, so you're right. We should explain a bit better here. This is the iteration k. This is the iteration k plus something. So it's another future iteration of the optimizer. But this is a spatio-temporal domain. And
I know, and that's the confusing part.
Yeah.
That you are making an argument about the difference in the behavior as the iteration evolve. But wait a minute, Yanis. But you are showing a plot that focuses on the initial condition, which has to do with the actual temporal dimension of the problem. That's the confusing part for me. It's as if you are blending the two different times, the fictitious one and the real one, to try to explain something, and that's what I don't understand.
I think I can explain a bit better in a sense that the network itself doesn't really understand what is time or what is space. You give it some PDEs, it has some variables, x, t, y, whatever, and then
I know, but your plots are in the opposite direction. You try to show that the actual time actually matters.
Yeah,
I agree with you that the network shouldn't know about the real time, but here you're trying. I think you try to make a point by using the opposite argument that the network does know about time because you're showing on the left plot the effect of the initial condition.
I think you should show the residuals, not along with the weights.
Yeah, this will be
when you say initial condition. Why should the initial condition on one side? I mean, I think that let me go back. I think that if you show the residuals that correspond to the weights at that moment in time, that might be more informative. I also think that, I mean, as Pano says, there's initial condition of the problem and there's initial condition for the weights. There are different things. Then it's a bit confusing. I also don't see why the initial condition of the problem should make a difference. I think that because of its initial condition of the problem, there's going to be, based on a random initial guess, a lot of very sharp residuals close to the edge. And it's the residuals that make a problem, maybe, not the initial condition itself. I'm just thinking aloud. I think just showing in parallel with these, what are the residuals that go along with the weights below them, that would be informative. Pano, do I make sense?
I mean, yeah, I don't even know if I make sense myself, but anyway, I do see the two different phases. So let's just stay with that and see what comes later. Yes, thank you, Sokratis. Yes, thank you.
This is the main point of this slide. It will be more clear in the later slides, as I will show the residuals as well, as you mentioned, which is more insightful, in my opinion. But just to address this short point here, the initial condition is basically the only source of information inside your domain, right? So all the points here are dependent on the information flow from this left boundary, right? So this thing, this shape here, you can see the shape also in the self-adaptive weights, right? And these are related to the maximum residuals. So initially, in the first few iterations, your network is trying to push as much information from the initial condition as possible. And that's why the residuals here are high. But I think it will be even more clear when we see the correlation of residuals and weights in the next few slides.
Okay, thank you.
This is Amaya from Brown. I have one question. So basically, on the left-hand side, whatever the weights you are plotting, it is basically the weight towards the end of fitting phase, right? So you have learned, some features of the solutions using the boundary or the initial condition, right? On left-hand side.
Yep.
But on the right-hand side, you have the weights in the diffusion phase. So of course, they are random, but how you are plotting these things? Basically, in the diffusion phase, you still have the information of the solution. I mean, in the fitting phase, whatever the features of the solution you can see, you can also see in the diffusion phase. But yes, in that phase, you are basically the standard deviation of the weights will actually, it goes above the mean values of the weights. That's what the bottleneck theory says, right? So how you are plotting the right-hand side? I didn't get that. I mean, my question is, right-hand side also should contain the same, flow features, which we can actually see here on the left-hand side, but with some noise. So that should be the diffusion phase.
Yeah, I'm not sure. I don't think there has been a correlation between the information bottleneck theory and pins so far. So how there haven't been these plots related to, what do you mean?
No, what I mean is, in the diffusion phase, we still have the information what we learned from the fitting stage, right? We are not losing that information. The only thing is diffusion phase will add additional noise. So, in my, what I think is the right-hand side should also contain the solution features, what we look in the left-hand side figure.
Not necessarily. And the proof for this is that even when we have this noise, quote unquote, the learning continues, and the learning actually achieves the optimal relative L2. This is not unwanted noise. That's what I'm trying to say, is that the weights start focusing on unregulated parts of the domain because they're trying to refine the understanding of the problem. Once we get the main features dictated by the initial condition, there's a second phase where actually learning continues and the weights are just chaotic and they don't follow the initial information flow. But let me go through the next slides, and
okay, thank
maybe I will clear any confusion on this. So just a brief introduction. The information bottleneck theory was a method which was firstly introduced by Natalie Thisbe in the late 90s. And
Neftali, sorry.
Yeah, sorry. It basically says that it's trying to explain how deep learning algorithms work. And it's doing that using the concept of mutual information. Basically, the gist of this is that the networks are trying to extract as much relevant information about the inputs with respect to the outputs, while minimizing the information about the inputs, basically. This is an open area of research, of course, and there's a lot of debate. So I decided to show some of the latest research on this, which was done in 2018, with a lot of discussion and cases discussing this. But as we can see, this is the SNR phase transition for an MNIST dataset. MNIST is a dataset for image recognition of handwritings, numbers specifically. And basically, the idea of this is that we have some signal. which is nothing else than the average gradients batch-wise of the network per layer. And the noise is the standard deviation of those gradients. And there are many definitions of this, but we chose to give this definition, which is also adopted in this specific paper. So the signal to noise ratio is basically showing that in the first few iterations, especially for the deeper layers, we get this sudden increase in the signal to noise ratio. And this is, according to the information bottleneck theory, when the network is actually trying to obtain the main feature of the solution. And after this point, after this bump, which is very apparent, and it happens in most cases that I've seen in the literature, this SNR starts decreasing. Of course, there's no correct SNR phase transition or evolution. This is very relative to the architecture, the conditions, the optimizer even. But the important thing to keep from here is that there is this sudden transition, there is this sudden bump of this signal to noise ratio. And this is what we try to investigate in our networks. So, as I mentioned earlier, we have these two phases basically, but I add a second phase, the transition phase in between to clarify where we see this abrupt change in the weights. And in these plots, we can see the signal, which is the average of the gradients per layer, the noise, and the signal to noise ratio. And it's exactly at this transitional phase where we can see a similar bump of noise in the SNR. And some of layers increase in this case, some of layers decrease, but the idea is that something changes here, and it's very obvious. And based on this theory, it's when the network is trying to refine the understanding of the initial features that were captured. And we also correlate this high to low SNR learning phases with the fitting of and diffusion of the RBA weights. This was very important for us. And another thing to mention here is that it's at this stage, this diffusion stage, the beginning of diffusion stage, the transition phase, where the network keeps decreasing the relative L2, right? This is the normalized comparison of the loss and the L2 as previously discussed in a previous question. So we can see that the rate, especially for the first few iterations, the first 100,000 iterations, the rate of convergence for the loss is quite lower than the rate of convergence for the relative L2. And it's after this transition that the network is actually achieving a good convergence for the relative L2 as well. And this is also apparent in the plots for the weights. So these are the network parameters for each layer. And we can see that after the transitional phase, we initiate the final convergence trajectory of those weights. Up until here, we're converging somewhere, but there's a different rate. There's an obvious different rate between the feeding phase and the diffusion phase of the network parameters. And it's when the training stabilizes, basically. At least that is our interpretation of this. Similar results we can see for the Helmholtz case. Here it's a bit more obvious that we start from this very ordered sinusoidal state. Just to mention here, this is a 6x6 case. Previously we showed a 1x4 just for the sake of comparison, but now
is this weights or residuals?
This is weights. We're only seeing weights so far.
Okay, all right.
But yeah, these are the weights for the 6x6 case, where we can see again this transition around 1,000 iterations, and this sudden bump in the SNR phase for all the layers. And after this point, we begin to go into a more diffusive disordered state. So I have some more videos to show, and I hope at least that I will clarify your previous points here. So we can see that, first of all, let me explain what we see here. I will pose it, let's say somewhere around here. Okay. So this is the prediction, how the prediction looks during the process of training. Bottom left is the convergence of the L2N loss. Middle top is the residuals here. Below is the SNR phase transition. Top right is the RBA weights. And bottom right is the network parameters. So as I previously discussed, the residuals are quite unstable, but it's not necessarily a bad thing. It means that we're skipping the local minima of the loss landscape. The RBA weights, however, they do a good job in dynamically varying themselves to attempt to stabilize the noise in the residuals. As you can see, they are able to capture the average trends during the training. But the interesting part happens somewhere around here, somewhere around 10,000 iterations, where you can see, okay, RBA weights and residuals are quite similar for this particular timestamp. But right at this point, we can see that the average trends captured by the RBA weights start to diffuse, start to have this transition. And also the weights start to initiate their final convergence trajectory. The SNR also has this bump, and the learning continues. And notably here, as previously mentioned, the relative L2 has a higher convergence rate than the loss.
Do you have a sense why apparently small changes in the weights create such huge changes in the residuals? There is like these flashes of huge residuals momentarily.
Yeah, that's what I tried to explain previously. We think that this is because we're effectively skipping through the local minima of the loss landscape. So as you go through, as you jump over a local minima, you will eventually find some high residual points, which are local minima. And sorry, you will find a local minima, and to go to a better one, you have to skip a peak.
I hear you, but why would it be so huge in the residuals and so small in the weights?
Oh, because the weights capture the average trends. And that's the main...
Maybe the color is also changing, is not fixed, because the prediction looks quite stable. So maybe there is a coloring, or no? What's the...
Bars are not the same for all these three plots. And you're right, the prediction looks very stable, but the residuals fluctuate. But this is basically, this has a different color map than the prediction.
But the color map is fixed during the training when you're showing this animation, because yeah, I see suddenly these bumps that looks quite bad, but then when you check the prediction,
I'm okay with the sudden flashes in the residuals because you jump over minima. But when you get to the new minimum, then this would have different derivatives and sensitivities, and I would expect the weights to also kind of... The weights also show a couple of times some big flashes, especially on the right. There is, I remember, a big red thing on the right. I'm just surprised at the big sensitivity of the residuals and the simultaneous small sensitivity of the weights. That mostly seems to happen.
Yeah, so that was by definition how we created these weights. We wanted to make some weights that capture the average trends. So as you see here, there are some flashes of residuals which happen for 1 or 2 iterations, right? They're very abrupt, they're very fast. So this will not affect the total RBA weights window that we're investigating. The RBA weights have this leaking term, the gamma, which basically keeps a lot of previous iterations as well. So you can think of this like...
So okay, now I understand, but it's because of the history, they don't have time to get affected.
Exactly.
Okay, now I get it, thank you.
And our interpretation is that they help because of that, because the residuals, if you want to achieve a really good accuracy, inevitably you have to have these instabilities in the residuals as you're scanning the loss landscape, which is also evident in the convergences, right? You have all this noise here. But to somehow tackle this noise, you need these RBA weights or other types of weights to help you with the stability. This is one of the points we made in the introduction of those methods. I don't know if that is clear.
Yeah, can I ask something here? So I see the layers. You have layer 1, which is the purple, and then layer 6, which is the deep blue, right?
Yeah.
So in the SNR, we see that there is a bump, like you say, in the SNR for the later layers, right?
Yeah.
But when we look at the actual weights, they go down fast for the later layers, right? If you look at the bottom right figure, the blue decays fast, right? The deep blue, unless you have inverted the color scheme or something for the, so how does these two figures reconcile?
So these are the absolute values of the weights. This is not correlated to the signs of this per se. So for example,
not the signs, but if the weights themselves become smaller, where does the increase in the signal to noise ratio come from?
Do you want to answer?
No.
So if the weights decrease,
so the weights, I see the deep blue line, right, in the bottom right figure, which is for the weights.
Yeah,
it decreases fast, right? After an initial increase, then it decreases fast. So by 10 to the 5th iteration, it has become much smaller than it was initially, right? But the signal to noise ratio for that layer actually has gone up for layer 6. So I was expecting that if the signal to noise ratio increases, the weight somehow will also increase.
Not necessarily. The signal to noise ratio is related to the gradients of these layers. These are the absolute values of the parameters. So when the SNR increases, it means that there is a high activity in the gradients of those layers. And that's why you can see this abrupt change in the values, but they can either increase or decrease. This depends on the architecture, the training.
But it looks like it is inverted, right? Whenever for the layers that you have an increase in the signal to noise ratio, you have correspondingly a decrease in the weights. So is there an explanation for that?
Yeah, that's what I'm trying to understand. So the weights can either go up or down.
Right, but I understand you say they can either go up or down, but here they seem to be following a very particular pattern, that the layers 4, 5, 6, where you have an increase in the signal to noise ratio,
yeah,
you have either a constant, remaining constant for the weights, or they become smaller. That's what I'm saying, that I understand that they can go up or down, but here they seem to be having a very specific pattern.
Yeah,
it's okay. I'll think about it more too. It's just I was asking if there was an intuitive explanation about why this is happening.
Maybe Juan has an intuition.
Yeah, well, actually, it's kind of like hard to come up with, like, I understand we can see like a clear pattern, but ideally, if this is just an idea, I'm not sure if that will be the exact answer for this question, but it's ideally what will happen if your overall mean of the gradients decreases. If the overall mean of your gradients decreases, maybe you would have a bit more chance to increase the standard deviation. So you will have more chance of noise, assuming that you have this interbalance, this interplays between signal and noise, right? So let's say that if the signal is low enough, then the low will be dominant, and then maybe that's the reason why we see like this.
Yeah, in other words, I think you cannot draw many conclusions just from the SNR on its own, because you can have the same behavior for different signal or noise behavior, if that makes sense. So yeah, maybe for this layer the SNR behaves this way because the noise increases, right? So the gist of this is that there is a very obvious change in the SNR. There's a very obvious bump compared to the previous feeding phase. Now,
Right. So there is a bump in the SNR, but the weights that become more important are in different layers, right? Are in the entry layers, in layers 1, 2, and 3. That's why you see them going up, the weights.
yeah.
So that's the discrepancy that is.
Yeah, I get your point, but
Yeah,
I'm not quite sure if I can say with certainty what is important and what is not, and how can one interpret this SNR on its own. It can be quite tricky. We try to do this, but I don't think you can draw conclusions just
Right,
from
but that's why I'm asking a question, because you seem to have put a lot of emphasis on SNR, and now SNR seems to somehow give these conflicting messages.
Yeah.
If taken together with the evolution of the weights.
Also, maybe, for example, let's assume in the sinus signal to noise ratio, what is in numerator, in the numerator will be the mean, right? The mean of the gradients themselves, right? And if we see what is actually, and let's say the mean of the gradients increases, then you will have some peak in the SNR. Let's think it that way. So, but how do you compute the gradients of these gradients? How do you compute it? You do your DL, DW, right? So if you have DL/dW and your dW becomes small, then then maybe if you're dividing by a smaller number, maybe you have a bigger number when you do that, assuming like this straight type of operation. Maybe it's related to that, but as Sokratis mentioned, it's quite hard to draw conclusions like.
Okay, that I could see how it could happen. I'm just asking if you have looked into it. What is the correlation between the two bottom figures, between the SNR and the weight, why they behave like that? I understand now your argument that if you divide by something which is the weight, right, which is smaller, then the SNR can go up. But okay.
It's a very, very useful remark, and we agree on that. But the first disclaimer I made about this SNR phase transitions was that we cannot draw immediate conclusions, and it depends on many factors, from architecture to optimizer to how different layers behave or contribute to the final prediction. But the important thing to keep from here, that they also mentioned in the initial paper, not the initial, the paper I showed initially, is that we have this very obvious bump, this very obvious phase change in the SNR, and that's how they treat it in the paper as well.
One of the modifications you showed at the beginning re-injected the first layer after each layer. You had the reference. That would also be maybe interesting to consider if you re-injected the first layer, in some sort of resonant fashion after each of the second layers. That would be interesting to see how it would change the figure.
Yeah, for sure. And especially, that's a good catch, because especially for these results I show here, as we mentioned in the paper, we don't use the modified MLP, because the modified MLP, as you saw in the convergence histories, it initiates a very fast convergence in the first few iterations. So just for the sake of presentation, we wanted to show this obvious change, that it was more apparent when we didn't use the modified MLP. But of course, these changes are very, very significant. They're very important for this phase transition. But I think, the important thing to keep from here is that the learning continues after the diffusive phase. And then we have the similar video for the Helmholtz equation, where in this case we show the cross sections of the lambdas of the RBA weights, basically, where you can see more obviously here that these cross sections follow a sinusoidal shape, which is dictated by the forcing term in this case. It's a sinusoidal shape. But right about this point, we start having a transition into a more chaotic and interesting pattern that forms in the residuals and the weights as well. So just to sum up, first of all, we show that it's possible to find a good accurate model and stable model and enhance it with bounded residual-based attention without any training. Of course, this is not to say that we can replace methods that we use ourselves, for example, the self-adaptive weights. This is just to show that it's possible that one can achieve a very good accuracy with using just the residuals in this manner we discussed previously. And also that the learning process of the benchmarks we tried reveals two distinct regimes. The feeding phase, where the model tries to learn the essential information about the input with respect to the output, and the diffusive phase, where it refines the understanding even further. And lastly, this observation, we believe that it could assist in enhancing the optimization performance and provide insights for the deep learning process of physics-informed neural networks and possibly even neural operators. And some of the future work we're currently dealing with is testing these RBA weights, the broader spectrum problems, understanding the reasons behind the bottleneck phase transition, and also possibly formulate a convergence criterion based to that information bottleneck theory. Because if you think about it, here we show all these relative L2 comparisons with the exact solution, but in most cases, in the real world, you won't have this facility, this comparison metric. You want to be able to know when your model has learned the best representation of the inputs to the outputs that it can. So it could be useful for this type of criterion. And I think that's all from me. Thank you once again for your attention, and we both will take as many questions as time allows.
I think we're already over the time.
Yeah, thank you both.
Yeah, thank
It
you.
was fun.
Thank you, Juan and Sokratis. Do we have any more questions, comments from the audience?
Yeah, I have one.
Yeah, go ahead.
Are the learned weights stable in that if you reinitialize after you've trained the network for a short time, what happens? Do they converge back to something close to the original state, or do they take a new trajectory?
Yeah, so this is an important question, and it was important for us as well. So we followed the relative literature, and we initialized with 5 random seeds for the benchmark results we showed earlier. So yes, they are stable, and they converge to similar order of magnitudes for the L2.
Sorry, I meant like mid-run as well. Like, for example, if you initialize the weights and then train the network for a while, and then you decide to stop training and then reinitialize the weights again, but leave the weights of the neural network intact and then resume training at that point?
Oh, I don't think that's a possibility, because the weights are related directly to the stage of training. And if you reinitialize the network, the training will be different. So I don't know if you get my point. Like,
well, I mean, I'd expect they'd come back to something near their state, but I just wondered if you had tried it. Maybe I wasn't clear. Is you train your network, and then at some point you decide you've trained enough, and then you reinitialize your weights, but leave the training state of the network intact, and then begin training again?
Yeah, no, I get the point. We haven't tried it, and I don't think we've tried it with self-adaptive weights either, but it's an interesting point. I'm not sure if it will work for the reason I mentioned, that these weights are very tightly connected to the state of learning and the specific iteration you're at. Because at this specific iteration, you encompass information about previous iterations as well.
Okay, thank you.
Maybe it will work, but I don't know if it will provide any further improvements.
Maybe if you want to do that, because everyone understands like some kind of weird, like you want to switch them on and off as you're training the model. That's what I understand. Please correct me if I'm wrong. That's what you want to do. But yeah, the problem is, like as mentioned, as Sokratis mentioned, the weights will be related to the specific iteration. And but maybe what you could do is like you stop them for a while and then you put them back in, but initialize this time, maybe not with zeros, but initialize with ones, maybe. But it's still hard to say because they are quite connected to how the training process is going on. So, but maybe I think it's a good way. Maybe it would be nice to try it sometime. Thank you.
But let me, sorry, if I'm saying nonsense, please tell me, but well, if you stop in the middle of training and just use the optimizer state, but initialize the weights, which is what was asked, isn't like training from scratch with both initializing the weights and the state, the optimizer state, like it's worse, it's like more challenging, let's say. And you, Sokratis, you just said you tried with 5 different seeds. So essentially it is supposed to converge to the same thing because you're doing something even easier. You are keeping the optimizer states, no?
But think about this: if you apply the diffusive weights, let's say you're at the diffusive state. Oh, sorry. Can you?
Yeah, sure.
Let's say you are somewhere here, right? And your weights are already very diffusive. If you try to apply these weights, reinitializing the parameters of the network and hence reinitializing the training process, I don't think you will get good results because you will skip essentially the fitting phase. Even if you could do that, I don't think it will work that well, if that makes sense.
Yeah, no, I understand. What he's saying is like you're saving the optimizer state. You are giving your network a head start. Like you're making it easier for the network to continue. Correct me if I'm wrong. Maybe I didn't. Maybe I misunderstood the question. But it sounds like,
yeah, sorry.
It sounds like your scheme should work even like better than like reinitializing everything. It should be easier for it.
Maybe we haven't tried, but I think you need to have some kind of order in the training process. You cannot just randomly initialize the weights at a random point during your training. I think it's important to start training from the initial iteration, both the weights and the network parameters.
I see. Okay.
I just had a comment on this plot itself that typically I see the loss is a lot less than the L2 error in the training.
Yeah.
So is that consistent? And what about if you do the testing error, is it similar to the L2 training error or is it somewhere in the middle or?
So you can see this, the L2 is the relative L2. It's basically the difference between your exact and the prediction, right? The loss is the loss of your residuals and boundaries. Sure. So the objective function.
Right.
And this is many orders of magnitude lower than the L2, just because of the square that you use in your objective function, right?
Okay. So you didn't sort of, okay, the square is there. Okay. But guys, I didn't. So you also have a plot afterwards, or what with the testing, like points which are not used in the training, right? That's typically what is done to show results, right? When you show testing error, right?
Basically, the L2 is testing because you're testing on a grid, and the grid is not used for the training.
Okay. All right. Thank you, Juan, Sokratis. So let's stop here and let's move to our second talk. Yeah, thank you for the presentation.
Thanks, everyone.
All right. Our second talk is given by 2 speakers, Ehsan and Umair. Ehsan Haghighat. I'm sorry. Could you teach me how to pronounce your last name? Haghighat, right? Like he is a research scientist at Carbon. Previously, he has held postdoctoral position at MIT and UBC, data scientist at GeoTab, and lead mechanics at Hexagon AB. He received his PhD from McMaster University, Canada, specializing in computational mechanics. His research interests include computational methods for the mechanics of solids and media, stochastic modeling and uncertainty quantification of engineering system, and machine learning applications in engineering analysis. Umair bin Waheed is associate professor of geophysics at Fahd University of Petroleum and Minerals. His research interests are broadly in the area of computational geosciences. Umair graduated from CAST with a PhD in Earth Science and Engineering in 2015. Prior to joining KFUPM in 2017, he was postdoctoral fellow at the Department of Geosciences, Princeton University. Welcome, guys. You may want to start the presentation.
Thank you, Shangan. Yeah, thanks everybody. My name is Ehsan Haghighat. This work is in collaboration with Umair bin Waheed and Professor Juan Diego Toscano. I think Umair is on the call. So questions related to seismicity, probably I will ask Umair to jump in. So the work here is an enrichment approach for enhancing expressivity of neural operators with applications to seismology. This is a work we did kind of last summer, but it took a while to write it down, and it is archived and recently submitted. So the main problem that we are looking at is predict earthquake localization. Where is the hypocenter of an earthquake given signals on seismic stations? But the approach can have applications in different problems. What are microseismic events? These are seismic events happens as a result of rock failure, typically caused by human activities due to mining, waste disposal wells, hydraulic fracturing, and so on. So the questions that are of interest are, when did the microseismicity happen? How big was the events, and where was the location? So where is the question that is addressed through hypocenter localization and our forecast here. And these are used, for example, to do monitoring and optimization of industrial processes. For example, if we have to shut down an injection well for oil reservoirs, so that if seismicity goes beyond certain threshold. Some conventional approaches are just using P and S waves observed at the surface and using some physics and data-driven approaches to correlate it with the hypocenter of earthquake. Also based on wave fields, there are classical approaches to that has been addressed, but they take long time to process the observations. There's also recently a lot of works on machine learnings, whether they are data-driven or even physics informed. So physics informed, you can use the pin solvers to solve the Iconal equation if you are only interested in travel time, or full wave field equations if you are interested in the wave propagation aspect, and inverse solve for the earthquake hypocenter. So that's just some background, and we have also looked at this problem in the past in the context of travel time calculations using Iconal equation. What is Iconal equation? So essentially it's a nonlinear first order hyperbolic PDE just listed here, and the source is where the travel time is 0, so that's the start of the earthquake, and T shows the time that wave front reaches certain point. So for example, at the source it's going to be 0, so that's the source. I don't know, a few seconds later the wave front going to be here, and so on. And then the velocity, another parameter, is essentially the material properties of Earth, right? So velocity of waves propagating through rock. Yeah, we have used it in the past in the context of pins, and just as a recap of our previous work. So with pins, you have a kind of neural network approximating the solution as a function of position, and solution being the travel time. And we form the losses, and we can solve it in a forward manner given a source location, or in the inverse part, if you don't know what is the source, but you have some observations on the surface, you can do the inverse solve to find the source, or even to optimize for velocity field, because that is also highly uncertain subsurface. So that was a work we did for forward problems, and also in inverse problem. That's a work by Umair and his team. So that's just a little bit of background, but now back to neural operator approach. So in this work, we want to build a surrogate model. So given different observations at the surface, to be able to instantaneously find what is the earthquake hypocenter. And we started with depot nets, and we found a little bit of challenge for this particular problem, and therefore the enriched depot net architecture. So just a little bit of context here. This is from Lou's paper. So for building operators using neural network, I think the most common architecture has been architecture A. We also used it for solid mechanics. Others have used it for fluid mechanics and everything. So the inputs can be coordinates and also material properties or other parameters to encode the operator. And then the output would be the solution. And then it turns out that in order to improve the learning capability of neural networks, dividing these two is much more impactful. There are also approximation theorem foundations for that, to divide the kind of sensor part to the branch network, and then have the trunk to encode the solution, and then a dot product at the end to build the operator. So just a little bit, one simple example here. This is from Paris's group, where they used physics-informed neural operator to solve the Iconol equation. So Iconol equation not only has application for this particular problem, which is travel time calculation, also the solution is a level set, so you can use it as a to find a distance function, and many other problems for describing fluid interfaces or moving interfaces, and so on. For this problem, the kind of the white shows the circle that the solution is 0, and changing the radius essentially changes the solution pattern. So this is a problem that was solved with physics-informed depot nets. However, in the context of earthquakes, we are interested to move this circle instead of just increasing and decreasing the radius. And the reason is that source location may change. So source location may be here, or maybe here, or maybe another position. And you can see this was the first example that we kind of studied whether this is equivalent to a constant velocity field, by the way. So as you can see, the predictions were quite bad from DeepNet, given a certain number of epochs with a high error. And we played a lot with the architecture and training time to see what happens here. Ultimately, what we came up with is an enrichment strategy, which is very simple, but just to reflect that the solution is changing. I'm going to describe it in a second. So this is the mathematical formula for DeepNet, right? So we have the branch components multiplied by the trunk components and summation. So essentially a dot product at the end. However, for the enriched architecture, what we were arguing was that, let's go back to the previous figure for a second. So if you check here, all of these, they are level sets, right? They are just a circle level set. All of these solutions, they are quite similar, except that the center of the solution is moving due to the location of the earthquake. So they, instead of being, I don't know, x squared minus x0, so only x0 component is moving. So dot product may not, it may not be easy for a dot product to reflect that aspect. However, a summation or a subtraction can easily differentiate between these two. So that's the main idea. So instead of a multiplication, we also add these additional features that we know it's because of the moving aspect. And then, but that product has the reducing capability. However, for example, addition or subtraction, they don't. Therefore, we need to add a weighted sum. And weighted sum is nothing but a linear layer. And if weights are 1, essentially we are recovering the dot product. So in other words, we are just adding applying these multiplications and adding a linear layer at the end. And then you may say that, okay, why a linear layer? Why not a full network? And that's exactly what we also thought. So extension of this was just to add a full network. So that's the change between these two architectures, and I'm going to show how it was helpful. So you can see that as soon as we add that.
Excuse me, can I ask a question?
Yes.
I am Kamal from Brown. In the previous slide, slide 13.
13, yes.
What is the input to the branch and the trunk and the output?
Yeah, the input, so it's based on exactly the setup of Paris. So the input was nodes on the circle. I think it was 20 or 30 nodes on the circle, something like that. I don't remember, this has been quite a while. But some nodes on the circle. So that's the input to the branch, and trunk is just XY coordinates.
So this is a forward problem, basically, you are trying to figure out. You are not trying to figure out the location of the earthquake. No,
not yet. This is a forward problem. We are building an operator using physics-informed, unsupervised training. So there is no data. We are just, the input to the branch is nodes on the circle. And then the output is the level set or distance function, whatever you call it.
Okay, thank you.
Thanks. Yeah, so essentially the change is just at this part and then adding the root network. And the connection, why we did that is exactly from that circle, because when just the center of the circle is moving, level set itself remains identical. So maybe the dot product is not the best way to reflect that underlying architecture. So when we do that, you can see that now we can kind of move the circle quickly, and it learns it very quickly. And not only that, we can now go to very point-wise source, because that's ultimately what we need for earthquakes. Whereas for DeepNets, if we keep reducing the radius, then essentially at some point it's just not able to get even a pattern. So the solution becomes completely wrong if we further reduce the radius. And just to show you where this applies, even if you use, so the previous case was a constant velocity model, and velocity comes in this, sorry, I'm going too much back, but velocity comes in this iconal equation as this. So this is like a material parameter. So when we have more complex velocity models also, yes, we have different, more complex solution, but still when you change the source, that's the most important one. So always solution moves with the source.
I'm sorry to interrupt. So here, so the X DeepNet is the enriched DeepNet, right? Or they're different?
Yeah, sorry, thanks for asking this. Yeah, we were using this extended or enriched. We were kind of going back and forth between these, but some of these figures are from from a while ago. Thanks for asking the question. Yes, X DeepNet and enriched DeepNet, they are identical. I mean the same thing. Yeah, and the application is not only for this seismicity problem. For example, if you have like a classical reservoir engineering problem, right? We have multiple wells usually. If you start injecting at one well, P223 in this case, or P20, fundamentally, what's going to happen if we forget about heterogeneity in the properties and everything, what's going to happen, we are going to kind of have an increased pore pressure around the well that we are injecting, and then a diffusion process. So this is going to be like moving the location where the solution is being perturbed. The same for fracture mechanics. So this is from some Data's paper. If we have two fractures and we are describing them with, for example, phase field, right? So if you check the true solution is just shifted because of the location of the fracture. There might be other side effects where stress concentration happens, if it's too close to the boundary or not. But if you forget about those details for a second, the main part is that as we move the location of the source, the solution also moves. So some other problems, the depot net is much better, the multiplication, I mean. For example, if we are at one fixed location, if we are changing the amplitude of force, then only solution at that location gonna be kind of increase or decrease and so on. So that multiplication is more important in those problems. Whereas if we are completely moving the location that we are imposing the boundary condition, that we are imposing the source, then this addition or subtraction might be more important. So that's the idea here. If we look at the loss function, so we can see that in both data-driven and completely physics-informed, no data, the enriched architecture works quite well, reaches very low losses, whereas the depot net cannot capture this problem or this solution. So some results. It's good that the previous talk went a little bit over time because our presentation gonna be shorter. So the first result is Marmouzi model. I'm gonna explain what that is, but essentially now we have this enriched depot net architecture. So the branch gonna encode sensor travel time observations at the stations on the surface. So that's the velocity model for Marmouzi field. And there are some seismic stations, and they're gonna tell us what was the travel time. So we feed that to the branch network. Yes.
Can I please ask a question? Sorry to interrupt. This is Adar from Brown. I was wondering if you have some like mathematical insight for that, because I do understand the depot net part where you have the branch projection into the trunk. It's kind of operates like an generalized Fourier projection. But when you do a summation or subtraction, it kind of like breaks the model. So I would think like maybe different vector space that instead of multiplication you have summation. Did you ever think about that? Do you have any comment about like what mathematical process is actually happening here?
We had a little bit of conversation with George and one of other co-authors of George. But so they are looking at it, but we, I cannot have more comments on that. So we haven't done more mathematical study what's happening here. But the idea is very simple, like from a practical perspective. This is the multiplication, which is exactly what you described, like a Fourier series. Whereas this subtraction is just how the solution is going to look like if you change the center of that circle and evaluate the level set, right? So the solution is going to be x minus x0. It's not x times x0. So that's the idea here.
All right, thank you.
So that's the Marmouzi field. And for example, we have some seismic stations at the top, and we are reading the travel time. So that goes to the branch network, and we obtain the solution. And from the solution, taking the minimum time tells us where was the hypocenter, because that is associated with zero travel time. So that's the main model here. So for Marmuzi, this is the velocity model, highly heterogeneous. We did a lot of experiments with simpler cases, smooth transitions, but then I'm just showing the results that we reported in the paper. So highly heterogeneous field, and for example, you can see that and the network is trained on variety of source locations and sensor observations, travel time observations at the surface. And for the inverse setup now, we get some observation and we want to find the source location. And these are the solutions and the source locations that we find. And there is a high accuracy in predicted source locations. So majority of points, they have less than 50 meters of error. An extension of this was velocity generalization, which is not only now we send in travel time observations at the surface, but we have another velocity branch, which is encoding the velocity field. So usually all of these inverse methods for hypocenter localization, they are regional. So for a region with a specific subsurface velocity field, they can do hypocenter localization. So now we are going beyond that. We are also building operator as a function of velocity field itself, which is highly heterogeneous and can vary for different locations. So this is more toward building like a global hypocenter localization operator that works for everywhere, essentially. Toward that, not there yet. So we have the observations at the surface, and then velocity field, and then the trunk still just encodes the location, and then we ultimately get the solution, and from there we can find the hypocenter. And for this case, we are using for a smooth velocity model, just by picking 4 random values around the corners and just randomly sampling the space. Again, very highly, the neural network training goes really well with very small error. And the higher errors are associated with the boundary. So we are not sampling the boundary as much. We were kind of sampling between 10% and 90% of the domain in each direction. So this also goes really well. Now we go to a highly heterogeneous case, which is the open FWI fault models. And this is like curved layers combined with a fault. And this is kind of the most complex case that we could think of. And there are 500 velocity models that should reflect kind of the state of material parameters at different locations near faults. And out of that 500, we use only 200 to train the network, but then we test on everything. And that's also what we observed, that the network does a relatively good job in predicting this source location given surface observations and a velocity model. So this is more now a global operator, which you just inject the velocity field for certain location on Earth and the surface observations, and you get the hypocenter of that earthquake. The error is a little bit higher here compared to previous cases. Previous cases, the error was very low, below 1%. And it's just because of the more complex velocity models, and the resolution of the velocity model is also coarse from open FWI. So if you have higher resolution images, I suspect the quality of predictions also might be better. Yeah, and that's the image that I showed before. So you can see that how changing a velocity model instantaneously we can find the source of the earthquake. And the code is going to be shared soon. We are waiting for the reviews, and with that, I think that's the end of presentation. So in summary, we propose an enrichment strategy for learning iconal operator, but it's not only limited to iconal. I can see, for example, for fracture mechanics, for well injections, and that addition or subtraction doesn't need to be just that. You can add other connections, and the name comes from a classical method, extended finite element methods, right? So where you enrich solution based on the characteristics that you expect from a solution. So we can encode other properties as well. So it doesn't have to be just those. We applied it for hypocenter localization. I have applied it for a few other problems, but yeah, working in industry, it's not easy to publish. So still those are sitting somewhere. We explored sensitivity to noise. This was quite surprising because DeepONet, we found that it's kind of not very sensitive to noise. So as we increase the noise on surface observations, it was able to get really good results. And this is very different from what we expect from classical methods in this area. And yeah, it is applicable to other problems. So our collaborators, Omar and team and others, they are looking at 3D problems and also missing sensors. If some sensors not signal, if the signal is perturbed, we discussed here, but what if some sensors are completely turned off, and that happens often. Yeah, and with that, thank you. And if you have any questions, I will take it here.
Thank you, Ehsan, for your presentation. Do we have questions from the audience?
Yeah, maybe I'll. First of all, thank you. Yeah, it's I mean, phenomenal results. I really like. It looks really good. I wanted to ask. So I understand the generic application of these. That's great, amazing. Like, but if we focus on the problem of like locating the location, the XY locations, how does it fare? How does the method fare with just trying to map images to XY locations, like the most naive way ever?
Oh, just getting images and finding the location?
Right, yeah. Doing a very, very simple regression problem, like regressing the X and Y locations.
So note that we don't have these T's, right? T's are outcome of neural network. And from this distribution, by taking the minimum, we find the location. So the location part is after T's. So T's is really the output of the network. So just by looking at velocity field, we don't know what is the wavefront distribution.
Right. No, I'm saying like, you can create a data set from velocity field instead of to the whole image that's shown here by X DeepONet. Like you can create a data set that takes from velocity field to XY, right?
Yeah. So then I can imagine that, yes, that is also possible if you consider all velocities and all locations and have a database, and then you can also just locate it quickly based on that database. The issue is that probably you're going to have a very large database, and that's where neural networks, they do that kind of compression for you. But I can imagine, yes, if you have large enough.
Yeah, sorry to interrupt, Ehsan, but also I think in terms of, we tried some things along those lines, but I think generalization is a big issue here. when you have the velocity model that is varying, which is not being done yet. And previously, people have tried this, the approach that Adar mentioned, but I mean, it's very limited to only the data set that you have for training, firstly. And you know, the thing is, then you cannot apply it to a different field where you are, let's say, having microseismic monitoring. And therefore you have to collect the data first, right? Specifically for that field, which means you have to wait a long time. Whereas something like this can be applied to a wide variety of fields where the velocity model is quite variable. Does that answer your question, Adar?
Yeah, I agree. I said in the beginning, like the generic application, I understand completely. Yeah, that's true, and I agree with everything you said. I was focusing on like this specific like problem mapping with from velocity fields to and yeah, it would be interesting because like you have the robustness, you can use that to make a big claim, right? If you take a model that actually does the simplified thing, the regression problem, you add a little thing that makes it completely wrong, and your model can digest it pretty well. That's a big win for you guys. Yeah.
Thanks for your comment.
Yeah, thanks for the comment.
Thank you.
Thanks so much.
Do you have any more questions? All right. Thank you, Ehsan and Umar, for attending this seminar, for giving this presentation. And so we end this week's seminar, and everyone have a good weekend ahead. See you next week. Bye.
Thank you.